Energetics 5. Standard enthalpy changes of reaction. Continued. If we recall, there's this little TIE fighter shaped thing at the top right. It's a superscript when you look at the enthalpy change, which tells us it's in standard conditions. And standard conditions are, of course, when the pressure is 1 times 10 to the 5 pascals or 100 kilopascals. All substances are in their standard state. So, which elements are in their standard state? Okay, so standard conditions, things are in a standard state. Let's have a look at these and see if we can tell if they're in a standard state or not. O2 gas, yep. Nitrogen, liquid, what do you think? That's right, it's a gas, so that would be wrong. Na plus solid. Does sodium exist as an ion in a solid form? That's right, it does not. Bromine liquid. Is bromine a liquid at standard pressure? It is indeed. Iodine. Is iodine a solid? Again, you're right, it is a solid. Silver. Silver is a metal, and of course it is a solid. Mercury. Liquid. Is mercury the liquid? It is. Again, you're right. Oxygen. Aqueous in its standard state. That would be wrong, wouldn't it? Oxygen is a gas. Water. Is water a gas? Standard conditions? Of course not. It's liquid. Down here we've got carbon, solid or graphite, and this is correct. It's often written as graphite because, of course, carbon can exist as a diamond or graphene or as a buckyball. Liquid iron, obviously not. Iron is normally a solid standard state. Mercury is a solid. Nope, as we've already said, it is a liquid in standard conditions. O3, well, ozone is a gas in standard conditions. However, oxygen, not ozone, is the standard state for this element in standard conditions. O minus gaseous, again, no, we know that oxygen is in fact a gas, and it's a diatomic molecule. Okay, standard enthalpy change of formation. A formation reaction is a reaction where 1 mole of a compound is made from its elements in their standard states. So here we've got hydrogen gas with oxygen gas giving water vapor. And so this is a formation reaction because hydrogen, the diatomic molecule, is the standard state, and oxygen, the diatomic molecule, is gaseous. So this is the standard state. What about the next one? Graphite is in its standard state, plus hydrogen is in standard state, diatomic gaseous form, and oxygen, diatomic gaseous form in the standard state. And so yes, this is a formation reaction. Here we've got nitrogen gas with hydrogen gas giving ammonia gas, so everything looks good, right? But what we've got here, we're making 2 moles of ammonia, and up here it says 1 mole of a compound. A formation reaction is a reaction where 1 mole of a compound is made, so this is not a formation reaction because we're getting 2 moles of a compound formed. Next one, we've got carbon monoxide gas giving plus oxygen gas giving carbon dioxide gas. So things look okay, everything's in its standard state. But 1 minute, what we've got here, carbon and oxygen. So this is a compound. It says here is made from its elements in their standard state. Okay, so carbon monoxide is a compound, not an element. So it's not a formation reaction because one of the reactants is a compound, not an element. The standard enthalpy of formation is the enthalpy change when 1 mole of a compound is made from its elements in their standard states. The symbol is delta H with a little circle on top to show its standard state and a little F for formation. Units, kilojoules per mole. And the standard enthalpy of formation data for organic compounds given in table 12 of the data booklet. For example, the standard state of formation for water vapour is minus 241.8 kilojoules per mole, and the standard enthalpy of formation for benzoic acid is minus 385 kilojoules per mole. You can sometimes rearrange an equation to find the standard enthalpy of formation of a compound. For instance, here, and we looked at this before, we're making 2 moles of ammonia, so this is no good. But if we just half everything, then we're only making 1 mole. So for half this enthalpy, we get the enthalpy of formation. And here we've got carbon dioxide gas giving us carbon in its standard state and oxygen in its standard state. So if we just reverse the thing, you're going to end up with the standard state of formation. So we're just sticking minus sign in front of the change in enthalpy in the standard state. Have a go at writing the thermochemical equations that represents these two. The standard state of formation of ethanol and for methylamine. You've got 2 minutes. Press pause. Good. Did you get this? I hope so. You can see that we've got ethanol, it's a liquid, and we are using carbon, diatomic hydrogen, diatomic oxygen, and we've got 1 mole of this. Okay. Here, standard enthalpy of formation of methylamine, sorry. We've got carbon, solid, we've got hydrogen diatomic gas, nitrogen diatomic gas, giving us methylamine. The standard enthalpy change of formation for any element in its standard state is defined as 0. So the standard enthalpy change of formation for oxygen gas, or for chlorine gas, or bromine liquid, they're all 0. Okay, this is true for hydrogen gas too, or iron as a solid, or graphite. These are all 0 because the standard enthalpy change for any element in its standard state is 0. Elements that are not at their standard state do have delta and do have standard enthalpy change of values. For instance, ozone, because it's not oxygen gas, has the standard enthalpy change of plus 143 kilojoules per mole. And iron, in its gaseous form, would have a standard enthalpy change of formation of 416 kilojoules per mole. Chlorine gas, 122. The standard enthalpy change of formation values can be used to find the enthalpy change for any reaction. So if you've got reactants here, we know the enthalpy change of reaction because they're products. And we can think of this here, the elements in the standard states. The standard enthalpy change of formation will give the reactants, or standard enthalpy change of formation can give the products. And we can use this cycle like we've done before. The standard enthalpy change of formation of elements to reactants plus followed by the standard enthalpy change of the reaction is an indirect route, which is the same as, gets you to the same place as the standard enthalpy change of formation of an element to the product. So that the standard enthalpy change of formation of reactants plus the standard enthalpy change of the reaction is going to equal the standard enthalpy change formation of the products. And so from this we can conclude that the standard enthalpy change of reaction is equal to the sum of the standard enthalpy change of formation of the products minus the sum of the standard enthalpy change of formation of the reactants. Okay, let's do an example. Example 1. Use standard enthalpy of formation data to calculate the enthalpy change for the combustion of propane. Well, propane reacts with oxygen to give us carbon dioxide and water. So we've got this propane plus oxygen giving us carbon dioxide and water. So let's put the elements in the standard state below here. We've got carbon, diatomic hydrogen and diatomic oxygen. So the standard enthalpy of formation of propane from these elements, followed by the standard enthalpy change of this reaction, which will be, we're making 1 mole of this, so it's standard enthalpy information times 1 of propane, and then we've got the standard enthalpy reaction. That change was the same as the indirect route, and it'll be equal to the direct route, which would be this, and it's going to be 3 times the standard enthalpy change formation of carbon dioxide and 4 times the standard enthalpy change of formation of water. So standard enthalpy change of formation of propane plus standard enthalpy change of this reaction is equal to the standard enthalpy change, 3 times standard enthalpy change of formation of carbon dioxide plus 4 times standard enthalpy change of water. We could just stick in the numbers from our data booklet, rearrange it to get the answer. Example 2. There's another approach we could take. We can use Hess's law and algebraically complete it. We've got the target equation here. Our propane, the combustion of propane to give carbon dioxide and water. The component reactions, we're going to write the formation equations for each compound in the reaction first. We know that we could do propane first, and that's carbon plus diatomic hydrogen to give us the propane, and would get the enthalpy formation from the data booklet. Then do the same for carbon dioxide, and then do the same for water. We don't need to do it for oxygen because that's already in its standard state, and so its enthalpy formation would be 0. It'll take no part in this calculation. So once you've written the formation equations for each compound in the reaction, as we have as follows, we can see how we need to change it so we can add them together. Well, the first one, we can see this is the formation of propane, and so this needs to be reversed, and there's 1 mole of this and there's 1 mole of this, so we just need to reverse it, so multiply it by -1, and so we just need to multiply the formation, the enthalpy change of formation of propane, multiplied by -1. Next we've got carbon and oxygen giving us carbon dioxide gas, and this is a product, so we're good, but we need 3 of them, so we just multiply by 3, and then multiply the enthalpy change of formation by 3 to give us -1,182, and oops, finally you can see that there's 4 waters here, it's a product, and there's 1 water here, product, so we're going to multiply the enthalpy formation of water by 4, multiply those coefficients, and then multiply the enthalpy formation data. Then we can add, first of all, cancel things out. Let's cancel the hydrogens out. Let's get rid of those carbons too. That's it, and add them together. And we've got our target equation, and then we'll just add those enthalpy formations together to get the overall enthalpy of combustion of propane. Next, approach 3, using a formula for delta H. This is, in my opinion, the most straightforward way of doing it. You've got the enthalpy change of reaction equals the sum of the enthalpy change of the products minus the sum of the enthalpy change of the reactants. Both of these are enthalpy change of formation. So, if you've got the reaction here, you can write out the equation and just plug in the numbers. So for the products, we've got carbon dioxide, so it's 3 times the enthalpy change of formation of carbon dioxide plus 4 times the enthalpy change of formation of water, because these are the coefficients here. Take away the enthalpy change of formation of propane, and there's just 1 of them, plus the enthalpy change of oxygen. Put in the numbers, put in the data from your data booklet. You can see actually the oxygen one is 0. Do the maths and you get your answer. So it's a quicker way of doing it, in my opinion. Example 2. Calculate the enthalpy change for this reaction using enthalpy cycle and enthalpy formation values. So you've got methane, gas, and hydrochloric acid giving us dichloromethane and hydrogen. So let's fill in the cycle. using this enthalpy cycle. We can see that we have to look at the enthalpy formation of methane, and there's one of them, so just times 1. Then the enthalpy formation of hydrochloric acid, there's 2 of them, so it'll be enthalpy formation of hydrochloric acid times 2. We've obviously got the enthalpy formation of the reaction going here. And with this side, we've got the enthalpy formation dichloromethane, and hydrogen is already in a standard state, so we don't need to include that. So the indirect route of going from the standard state elements via the reactants to the products includes the enthalpy formation of these reactants and the enthalpy formation of the reaction. And this indirect route is equal to the direct route, which is the elements enthalpy or formation of the products. So we're going to write that down below. Enthalpy formation of methane plus 2 times enthalpy formation of HCl plus the enthalpy of the reaction. It gives us the standard enthalpy change of formation of dichloromethane. Rearrange that, actually stick numbers in first, and then rearrange it and do the maths. Okay, approach 2, we can use Hess's law again, and the algebraic route. We've got the target equation here, methane plus hydrochloric acid, gives us the dichloromethane. You write your component reactions, and write the formation equations for each compound in the reaction. And then we'll look at ways that we can add them together to get this target equation. Well, let's have a look. We've got carbon this side, that's no good to us. Methane is a product here, but it's a reactant here, and it's a 1, 1. So multiply that by -1. And we need to change the sign there. See, we change the sign because we multiply by -1. Next, we've got HCl here, and it's a product, but it's a reactant over here, and there's 2 in the target equation. So we need to multiply this by -2. Reverse this, multiply by -2. And multiply the coefficients, and then we'd multiply this figure here by -2, giving us a positive enthalpy change. And finally, we've got the dichloromethane is a product here, it's a product here, so it's all good, and it's a 1 to 1, so we don't need to do anything with it. Right, let's cancel out those hydrogens first. Then we can cancel out the carbons and the chlorine gas. Add them together, we get our target equation. Then you can add the enthalpy changes together to get the enthalpy change of this reaction. Then we're going to do the quick way using the formula. The sum of the enthalpy change of formation of products minus the sum of the enthalpy change of formation of reactions gives us the enthalpy change of the reaction. And so we just plug in the numbers. We've got the enthalpy change of dichloromethane plus the enthalpy change of hydrogen, which as we know will be nothing, or 0, minus the enthalpy change formation of methane plus 2 times the enthalpy change formation of hydrochloric acid. And then stick in the numbers, and remember to include your units. Okay, to summarise for the enthalpy change of formation, there's 3 ways we can do it to find the enthalpy change of reactions. We can draw an enthalpy cycle to understand the routes taken, and it's the enthalpy formation from the standard state elements, reactants, via the enthalpy change of the reaction. That's the indirect route, is the same as going from the enthalpy change from the standard state elements to the products. You can use Hess's law by writing the formula equations for all the compounds in the question, then manipulating the formation equations so that they add up to target equation, or we can just use the formula for finding any change in enthalpy reaction using standard enthalpy change of formation values. Next, standard enthalpy change of combustion. So the standard enthalpy of combustion is the enthalpy change when 1 mole of a substance burns completely in oxygen under standard conditions. Simple, It's delta H with the little circle at the top, and a little C as a subscript for combustion. Units are kilojoules per mole. They're given on table 13 of the data booklet. Here we've got propane and oxygen being fully combusted to give carbon dioxide and water, and we've got the standard enthalpy change of combustion as minus 2219 kilojoules per mole. Here we've got ethane reacting with oxygen to give us just carbon dioxide and water. And note that the definition for the standard enthalpy of combustion states that 1 mole of fuel is used. Okay, oops. This means that the fractions may be needed when balancing the equation. So if we've got 1 mole of ethane, we're only going to need 7/2 moles of oxygen, and so fractions will be involved quite often. The standard enthalpy change of combustion values can be used to find enthalpy change for any reaction, and we can use one of these cycles again. The reactants can be completely combusted to give combustion products, and that would be the standard enthalpy change of combustion of reactions. And the products could be totally combusted, the standard enthalpy change of combustion for products, to give these combustion products, which are carbon dioxide and water. The reactants going to products is obviously the enthalpy change of reaction. So the enthalpy change of reaction, then the enthalpy change of products being combusted, is an indirect route, which gives us the same thing as going from the reactants directly to the combustion products of these reactants. So the standard enthalpy change of combustion of reactants is equal to the standard enthalpy change of the reaction plus the standard enthalpy change of combustion of the products. And so we can get this nice helpful equation here, that the standard enthalpy change of reaction is equal to the sum of the standard enthalpy change of combustion of the reactants minus the sum of the standard enthalpy change of combustion of products. Great. Okay, let's use standard enthalpy of combustion values to predict the enthalpy of formation of glucose. We've got standard enthalpy change of reaction equals the sum of the standard enthalpy change of combustion reactants minus the sum of the standard enthalpy change of combustion products. And then we've got the formation of glucose, graphite plus hydrogen plus oxygen. Let's stick in those numbers. We've got 6 times the standard enthalpy change of combustion of carbon plus 6 times the standard enthalpy change of hydrogen, standard enthalpy change of combustion of hydrogen plus 3 times the standard enthalpy change of combustion of oxygen minus the standard enthalpy change of combustion of glucose. Stick in the numbers and do the maths to get your reaction, to get your answer. Do notice that the standard enthalpy change of combustion of oxygen is 0. Okay, use standard enthalpy change of combustion values to predict the enthalpy of formation of glucose. Let's do an energy cycle. So let's stick it in there. We've got the carbon, hydrogen and oxygen giving us the glucose, and the combustion products, the combustion products of both the reactants and the products, is carbon dioxide and water. So the standard enthalpy change of this reaction, which is of course the standard enthalpy change of formation in this case, plus the standard enthalpy change of combustion of glucose, is just an indirect route, which is equal to the standard enthalpy change of combustion of carbon plus the standard enthalpy change of combustion of hydrogen, and obviously it would be 6 times the carbon and 6 times the hydrogen. Oxygen, as I said, we don't need because the standard enthalpy change of combustion for oxygen is 0. Okay, you can just plug them in to the formula. We've got 6 delta HC plus 6 delta HC hydrogen is going to give us the standard enthalpy change of reaction plus the standard enthalpy change of combustion of the glucose. Plug in the numbers from your data booklet, rearrange it to get the answer. So to summarize, calculating the enthalpy of reaction values from standard enthalpy values, we can use standard enthalpy of formation values, and this, we know that the elements, we can look up in the data booklet to see the standard enthalpy formation of reactants and the standard enthalpy formation of products. or we can look up using standard enthalpy of combustion values, and the reactants combust to give carbon dioxide and water, and the products will combust to give carbon dioxide and water, which means we'll have 2 bits of information which is sufficient to then work out the standard enthalpy change of the reaction. The equation we use for formation values is the standard enthalpy change of reaction equals the sum of the standard enthalpy change of formation of products minus standard enthalpy change of formation of reactants. Conversely, the standard enthalpy change of reaction when using combustion values is the sum of the standard enthalpy change of combustion of the reactants minus the sum of the standard enthalpy change of combustion of the products. Okay, so in formation values, you're taking away the reactants. In combustion values, you're taking away the products. Splendid.